Hello and welcome back to Automata Grammars and Computability. We are at non-regular languages, and then next time we'll probably talk about regex. Set notation is more expressive than DFAs. Let me explain what I mean. Let's say I write this example of a language which is a to the n concatenated with b to the n for n greater than 0. In other words, it's the language with an equal number of a's and b's. It turns out that there's no way to draw a DFA or NFA for this, and we can't define this language with regular expressions either. This starts to indicate that there's a hierarchy of languages, so languages that you can't do with a DFA, but you can still describe. And so now we want to start thinking about languages that aren't regular, things that don't have DFAs for them, and how we want to describe them. Okay, but how do you know that a language isn't regular? You could try to prove that there is no DFA or NFA that will accept it, right? So you could try to draw the DFA and then just say, well, it's impossible. A better way to do this, though, is to find a way to characterize all regular languages and then show that the language you have doesn't meet the criteria. One way to do this characterization is with something called the pumping lemma. The pumping lemma says something about the structure of all regular languages. Basically, a regular language is either a finite set of strings or there is at least one loop that can be quote-unquote pumped an arbitrary number of times. In the latter case, the regular language is going to contain all strings that contain 0 or more repetitions of the loop. Let's look at an example to convince ourselves that any finite set of strings is a regular language. Let's consider a language that has only one word in it. Let's say that the alphabet is the letters A, B, and C, and let's draw the DFA that accepts the word A, B, C. So please pause the video and give this a shot. You should have come up with an answer that looks similar, maybe not exactly like this. I have 4 states which I named Q, R, S, T. The initial state is Q, and then on letter A it goes to R, then on letter B it goes to S, and then on letter C it goes to T. And then of course, to actually make this a DFA, you need to ensure that on other letters that this string will go to some sort of fail state, and if it continues, because we only have one accepting string. But the main point here is that we need at least 4 states to be able to accept a string that has these 3 letters as in order as the string that it accepts. Okay? Let's expand that example, and let's say we want to draw a DFA that accepts the string ABC and then BBC star. So ABC at the beginning and then BBC repeated as many times as you need to. Think about for a moment how you need to modify the DFA that we had previously to be able to accept this new string. Basically, you're going to add a loop to the previous DFA. Whereas previously we had basically these 4 states, now we're just going to add a letter, the transition on B, back so that we can accept B as many times and go back as we need. And what you might notice as well is that the number of strings that this DFA accepts is now infinite, countably infinite. So the size of this regular language is now countably infinite. The takeaway there is that any infinite regular language has a loop in its DFA. Things like the Kleene star make it possible to accept an infinite number of strings, but a DFA only has a finite number of states. And of course, with Kleene star, you still have a regular language. I'm going to give you one more example to work on to get a sense of these loops. So draw a DFA that accepts the string AB followed by CB star followed by C. So note that this is 0 or more repetitions of CB. And the answer will not be available here, but I recommend giving it a try and then checking to see if it's correct later on. Before we continue talking about the pumping lemma and its characterization, I want to talk about something that's a little bit more general, something known as the pigeonhole principle. The pigeonhole principle states that if there are, 9 holes to put pigeons in and you have 10 pigeons, you are going to have a hole that has at least 2 pigeons in it, which appears in this image that I have here. And by the way, it doesn't matter how you spread the pigeons out, there's always going to be a hole that has more than 1 pigeon in it. More generally speaking, if there are n pigeonholes and n plus 1 pigeons, then there exists at least 1 hole with 2 pigeons. So the reason that this relates back to the idea for regular languages, by the pigeonhole principle, if you have a sufficiently long string in a language L, then to be able to accept it, it has to repeat some state in the finite automata, which is going to create a cycle. And this is going to be the big idea that's going to help us with using the pumping lemma. All that to say, let's go ahead and talk about the definition of the pumping lemma. If A is a regular language, then there exists a number p such that for all strings s in A where the length of s is greater than or equal to p, s can be divided into 3 pieces, x, y, z, such that for any I greater than or equal to 0, x, y to the I, z is an A. 2, the length of y is greater than 0. And 3, the length of xy is less than or equal to p. In other words, let's break down each of these 3 qualities. The first one says that there is at least one loop y. So x, y to the I, z means some string x concatenated with I copies of y concatenated with some string z. The fact that I is there indicates that there's a loop. The fact that the length of y is greater than 0 means that it's not an empty or epsilon loop. And because I'm requiring that xy has a length less than or equal to p, that means that there's going to be a value of p where the string xy is not longer than p. So this kind of restricts where that loop is. The pumping lemma has several different moving parts to it with those different quantifiers. So let's break it down and look at first the pumping lemma from an automata theoretic point of view. We know that if a finite automaton accepts an infinite language, then the automaton has to have a loop in it somewhere. That's due to the pigeonhole principle. So now let's say that there's a DFA with p states in it. And let's consider a language L that has a string s in L where the length of s is greater than or equal to p. This is what the pumping lemma has as its setup. Now, you can break s into pieces of substrings, which these substrings I'm calling x, y, and z. And we can say that the properties of x, y, and z are as follows. X is the path that brings you to the loop. Y is one iteration of the loop. And z is the path out of the loop that gets you to a final state. Let's look at an example with a drawing of a DFA. The DFA that I have here has three states, Q, R, and F for final. And Q has an arrow out on it on X, and then R has an arrow out on it on Z to the state F, and R additionally has a loop on it for Y. You can check that this DFA has the properties that I required from the pumping lemma. First, Y is not epsilon. The thing I drew is literally a DFA, so I know that that's already true. So I have a loop on it where the length of Y is greater than 0, or in other words, Y is not epsilon. I also have the condition here that xy is less than or equal to p, because in this case I have three states, and x and y together is only length 2. And that works out for us because y is the start of the loop. And the final condition that I have true here is that xyz is in L, and that's because there is a loop at all. And because of that loop, I know that x, y to the I, z is going to be in L. Right, so this is just a drawing that shows basically the same thing that the pumping lemma was saying. And it also gives this example where I've literally set the string S to be the letters X, Y, and Z. Let's break it down a little bit more. So I'm literally saying that the string is X, Y, Z. So in this case, the length of S is equal to 3. And we can relate this back to the pigeonhole principle. If we consider the path associated with S, we see that the length of S is greater than or equal to P, and so the number of nodes on the path is at least P plus 1. In this case, the length of S is 3, P is 3, and there have to be at least 4 nodes on the path to read the string S in. So let's take a look. I have the start state, which is Q. I'm going to read in X, which will take me to R. I read in Y, which takes me to R again, and I read in Z, which takes me to the final state. Here I see that the number of nodes that I have to read on the path is at length at least 4, because the string was of length 3. We can conclude that there must be a state that appears twice. In other words, a hole that has 2 pigeons in it. Now that we have this understanding of the pumping lemma, let's talk about how we actually use it in practice. Generally, the pumping lemma is used to show that a language L is not regular because it doesn't have the properties that we want. And the way that this is going to work, proof using the pumping lemma, you will say a proof by contradiction. By the pigeonhole principle, any sufficiently long string in L must repeat some state in the DFA and create a cycle. We pump the cycle to lead us to a string that shouldn't be in L and yield a contradiction. That means that L is not regular. Okay, this slide just shows the general structure of the proof, but let's break this down a little bit more. Let's assume for a language L that there's a P that exists that works. Then you are allowed to cook up a string S in the language such that the length of S is greater than P, and such that for any X, Y, and Z with S is equal to X, Y, Z, and the length of X, Y less than P, there is a number I such that X, Y, I is not in the language. Another way to view the pumping lemma for proving non-regularity is this game-like point of view. Let me write out what I had in words, but put the mathematical symbols for exists and for all on here. So I have the exists P such that for all S in A, there exists an X, there exists a Y, and there exists a Z, such that for all I, blah. Notice how we have this structure of going exists and for all in this alternating way. Alternating quantifiers describe games. You can literally think of this as playing against an adversary who is going to give you a language and claim that it's regular. Now you get to pick a string S in that language. You get to pick whatever you want for S. Now, this adversary is going to decompose the string into 3 different parts, X, Y, Z, and they're going to give it back to you. Now, you get to pump the middle to get a string not in the language and win. In other words, you take the X, Y, Z you've been given and figure out an I on the Y such that if you repeat I many times, then it should not be in the originally described language. You'll note as well that because of the extra constraints, the part that you're going to pump will appear in the first P characters. So that just has to do with this requirement that the length of XY is less than or equal to P, which just makes it easier to show that if you pump where that loop is going to be. And in this way, you defeat this adversary. Finally, let's go over a proof to show why a particular language is not regular using the pumping lemma. Let's use the example we had at the beginning. X is equal to a to the n, b to the n for n greater than 0, and prove that it's not regular. Proof. Assume for the sake of contradiction that x is regular. Let p be some arbitrary value. Now, you get to pick a string s, which is equal to a to the p, b to the p. By the pumping lemma, a to the p, b to the p is equal to x, y, z, where y is not epsilon, the length of xy is less than or equal to p, and for I greater than or equal to 0, x, y to the I, z is in x. Good. We picked a string, and we know that the string is longer than length p because of how we picked it, and we're also using those requirements that we have from the pumping lemma to break it up into these substrings x, y, and z. Now what we're going to do is pump y the right number of times to get a string not in the language. Let's go ahead and break down S and think about what x, y, and z have to look like. Remember, I have the requirement that x, y has a length less than or equal to p, and also that y is not 0, so it has to be at least 1 letter long. S is a to the p, b to the p, which is also x, y, z. And so I can write a bunch of a's in a row and a bunch of b's in a row. And because of the requirement that x, y is less than p, I see that y must be somewhere in those first set of a's. It can't have any b's in it because then you'd have p-a's and then some number of b's, which would be a string longer than p. And furthermore, I know that y has to have at least one a in it because of the requirement that y is not equal to 0. Now, because of all this, you can conclude that y has to be a string of all a's. And now let's do the pumping part. Because we can write y as a bunch of a's in a row, we know that the string a to the p, b to the p has to look something like a to, let's say, the ix, whatever that number is, could be 0, a to the iy, and then a to the iz, and then followed by some number of b's, right? PBs. Now, it could be the case that y appears earlier in the string, that x has a length of 0. None of that really matters, but the point here is that I have this part which is x, this part which is y, and this part which is z. And I have a rule that ix plus iy plus iz is exactly equal to p, and that iy has to be at least 1. So now, if we pump this string, and let's go ahead and pump it 0 times. In other words, let's look at xz. Well, the string xz is a to the ix, a to the iz, b to the p. Well, because I killed iy here, and I knew that it had to be at least 1, I now know that ix plus iz is less than p, strictly less than p. Well, guess what? xz can't be an x because it has fewer a's than b's. But I was able to obtain this string by pumping the string that I had with s. So xz contains fewer a's than b's and therefore can't be in the language, but we were able to pump it, and the string that we started with was definitely in the language, and therefore we have reached a contradiction, and we can say, turns out, x is not regular. Great. So this is where this video ends, and there will be some more examples of non-regular languages and using the pumping lemma that you should try on your own. So what I'll leave for you is this exercise, which is this language of palindromes, which is W followed by the reverse of W for W in 0, 1 star, and show that it's not regular. So this is palindromes where you have an even number of letters total. So again, use the proof by contradiction and the pumping lemma for regular languages, following a similar system that we had before. That's all I have for now. So thank you for watching.